Hello and welcome to our video about how we performed practical exercises 3 and 4, where we will be working with complex digital circuits. In the first part, we built a circuit with a data selection IC known as a demultiplexer. In the second part, we built a circuit featuring a 555 timer clock and counter leading to a 7-segment display. In the third part, we used the circuit from part 2, but connected the 555 timer clock to a serial connection of D flip-flops to create a shift register. A demultiplexer is a digital switch with a single input and multiple outputs. It is also called a data distributor or a DMUX. A demultiplexer of 2 to the power of n outputs has n selected lines, which are used to select which output line to send to the input. There are 4 types of demultiplexers with 1, 2, 3, or 4 selected lines. For comparison, the picture here in the right corner shows a multiplexer on the right and a demultiplexer on the left. In our experiment, we used a 1 to 16 demultiplexer, which has 4 selected lines. 1 to 16 demultiplexer has 1 input data, 4 selected lines, A3, A2, A1, and A0, and 16 output lines, Y0 to Y15. This is implemented using AND and NOT gates. This is a truth table that shows the operation of 1 to 16 demultiplexer. The push buttons are the selected lines that are represented by A0 to A3. When we push the buttons, the binary number becomes a 1. The binary values in the table are determined by binary addition, which was shown on the previous slide. When we connected the LEDs to ground through a resistor instead of to the VCC, the lights that were supposed to be turned on when connected to the VCC were turned off, and vice versa. For example, if all inputs are low, the first row on the left table, and the LEDs are connected to ground, the first LED should be turned off and all the others activated.
The 555 timer is not named after its inner circuit, which is surprising because it has 3 5K ohm resistors which are connected in series and used as a voltage dividers. It does the same job as the push buttons have done so far, generating clock pulses. It can be used to provide time delays as an oscillator and as a flip-flop element. In a stable mode, the 555 timer acts as an oscillator that generates a square wave. The frequency of the wave can be adjusted by changing the values of 2 resistors and the capacitor connected to the chip. A stable means that the 555 can operate repeatedly. It will switch on, then off, then on, then off continually. The 7-segment display is a form of electronic display device for displaying decimal numerals that is an alternative to the more complex dot matrix displays. The 7-segment displays are of 2 types, common cathode and common anode. The internal structure of both types is nearly the same. The difference is the polarity of the LEDs and common terminal. Here you can see the truth table for common cathode 7-segment display that shows the individual segments that need to be illuminated in order to produce digits and characters. The truth table for common anode 7-segment display is exact opposite. In part 2, we built a 7-segment display driven by a 555 timer and a 4-bit counter. The clock pulse is passed to the 4-bit counter, which is then displayed on a 7-segment display. We connected different capacitors to the circuit, which gave us different frequencies. Here you can see the equation we used to calculate the frequency of the wave that the 555 timer generates along with our results. The function of our circuit with the 100 microfarad capacitor and disconnected push button is the same as with the push button when we are not pushing it. Our circuit counts from 0 to 9 in a moderate phase. However, if we connect our button and push it, the counter stops. Then we extend the 100 microfarad capacitor for each of the other listed. We notice that the more capacitance, the slower the counter. This makes sense because the more capacitance, the more time it takes to charge and discharge the capacitor.
The D flip-flop is a modified set-reset flip-flop with the addition of an inverter to ensure that inputs S and R are never equal to 1 at the same time. The basic D flip-flop has a D input, a clock input, and outputs Q and Q0. The D stands for data. This kind of flip-flop stores the value that is on the data line. The Q output always takes on the state of the D input at the moment of a rising clock edge. It is called the D flip-flop for this reason, since the output takes the value of the D input or data input and delays it by 1 clock count. The shift register is a type of sequential logic circuit that can be used for the storage of the transfer of binary data. It is a serial connection of D flip-flops. The flip-flops take information from previous flip-flops, display the result, and then carry it on to the next flip-flop. They are commonly used in converters that translate parallel data to serial data or vice versa. There are 4 types of shift registers: serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. We used serial in, serial out shift register. These are what the results should have looked like. In our case, parts 1 to 3 went well, but part 4 did not give the expected results. Part of Practical 4, we built a photoplethysmogrifier. In the second part, we built a 7-segment display, now driven by the photoplethysmogrifier and a 4-bit counter. Because the skin is so richly perfused, it's relatively easy to detect the pulsatile component of the cardiac cycle. This is done through an infrared light emitter and a photodetector that picks up the light that scatters off deoxygenated hemoglobin in nearby blood vessels. The resultant signal can be split into a DC and AC component. The DC component of the signal is attributable to the bulk absorption of the skin tissue, while the AC component is directly attributable to variations in blood volume in the skin caused by the pressure pulse of the cardiac cycle. In part 1, we construct a circuit that filters this infrared signal and employs the AC component peak to light a LED, which will therein serve as an indicator for the heartbeat. The photo to the left shows the components we used for this exercise, and the photo to the right shows how we put the first part of our circuit together. However, we didn't use the transistor and the 150 ohm resistor. Next, we filtered and amplified the V-sensor output. We set up a passive high-pass filter and then an active low-pass filter with enough gain for the signal to be able to drive the eventual LED. A high-pass filter passes high-frequency signals and blocks or impedes low-frequency signals. A low-pass filter passes low-frequency signals and blocks or impedes high-frequency signals. We know that the heartbeat will most likely have a frequency between 0.7 and 2.34 Hz, so we choose that as our cutoff frequency for the filters. The passive high-pass filter cancels out frequencies lower than 0.7 Hz, and the active low-pass filter cancels out frequencies higher than 2.34 Hz. Here you can also see the equations for finding the different resistors and capacitors for the filters. Here we have our calculations for the different resistances and capacitors for the high and low-pass filters. Now our circuit looks like this. Once the filters are added, the circuit is filtered, and we need to amplify the signal once more with another round of passive high-pass filters and active low-pass filtering. We use the same resistors and capacitors as before, using the one remaining resistor for the LED, 1 kΩ, giving a total gain of 101 times 101, that is 10,201. The 5K potentiometer is a variable resistor that changes to fit each individual's heart rate. We added the following schematic to complete our circuit and tested the PPG with each group member. The signal was very sensitive, so it was important to keep our finger very still. For part 2, we used our successfully built PPG as a replacement for the 555 timer we built in Practical 3. We also added a decade counter to keep track of our heartbeats. 2 push buttons were also added so we could reset our counts. Here we have our complete circuit with the most important components tagged in the photo. Using our device, we took turns measuring each other's resting heart rates in beats per minute. These are our results. Our device picked up Esther's and Kolbrún's pulse much easier than Guðbjörg's, so we had to measure her pulse a few times. Each member of our group performed 10 burpees, and straight after, we measured our pulse using our device. It's quite clear that our device picked up the increase in our heart rates and that by performing exercise, our heart rate increases.